Hello everyone. In this episode, I want to talk about what are the distributed hash tables and their use cases in the real applications. Then later on in this video, we'll try to understand what is consistent hashing and their use cases in real life. And we'll also try to run some of the examples where consistent hashing can actually be useful. And whenever you're trying to build any backend application, in what all scenarios you can use consistent hashing, which will reflect positively in your design interviews, and what are the scenarios if you pick consistent hashing, then it might reflect badly in your design skills. So let's get started. So the core concept of consistent hashing is the distributed hash tables. Distributed hash tables. So before understanding distributed hash tables, let's try to understand hashing. What is hashing? Because it's really important to understand the hashing and what is the core concept that's used in hashing. So in very simple terms, hashing is a powerful concept which allows you to search for a key in a particular data set. So let's say if you want to perform certain operation, let's say if you want to search whether this key is present or not, or have you encountered this key or not, then you can, with the help of the hashing, you can basically search this in constant time. Okay, so hashing has basically three major components. So the first one is the hash tables, and this hash table is the one or the container which actually stores your key value pair. The second one is the hash function, and this hash function basically takes your key and tries to map this key into the hash table where this key can be stored, and this function is a forward hash function. Forward hash function. Why? Because it takes your key, right, and then tries to give you a hash value out of it, which maps to this range where your hash table ranges. Let's say your hash table is of size L, then you will have total n minus 1 indexes. Then this hash function will basically map all of your keys that you're trying to insert into this hash table between this range 0 to L minus 1. And the last one is obviously actually the key value pair which you are trying to store, right? So these are the three major components of any hashing, and this hashing is can be implemented using these three. So if you use C++, you know you have the hash tables in C++, which is unordered map. In Java you have hash, I guess, and in other languages as well. In Python you have dict. So in almost every language you will find these hash tables. So yeah, so let's see in practice how do we actually insert or fetch keys from the hash tables. So let's say your hash table is of size 10, correct? So you will have, and right now we are trying to implement hash tables with the help of arrays. 1 2 3 4 5 7 8, I mean not here, 8 and 9. So let's say you first want to insert key 1 which has value 3, correct? So, and let's say your value was 8, so you wanted to insert 3 and 8. This is your pair, key value pair. Now the simplest hash function. So first thing that we need to be able to hash any key value pair, right, we need hash tables which we allocated here. Then we need a forward hash function, right, and this hash function will take your key and will give you a value, right? So in our case, let's use the simplest hash function, which is taking the modulo, and this is your size of the hash table, so which is 3 mod 10. So what it does, it gives you the position where you should insert this key in the hash table. So what you'll do is you'll put here 3 and 8. It says at index 3 you inserted key 3 and value 8. Now let's say you have another key value pair. So let's say you want to insert 5 and 10. Then what you'll do is we'll again apply the same hash function. So key is 5 modulo 10. So 5 modulo 10 is still 5, correct? So here we'll simply insert this key 5 modulo 10. Now if you want to fetch, let's say you want to quickly check if you ever inserted key equal to 3. So again you will pass your key through the same hash function. So 3 mod 10, you will get 3, right? And then you come into the hash table and you see in this position you have a key, right? So you return this 3 and 8, which means your key is 3 and its value is 8. Now let's say you try to insert another key, which is key equal to, let's say, 13. So what happens in this case? Now if you run this key through the hash function, so you get 13 modulo 10, which is 3, correct? Now this place is not available in the hash table because 3's place has already been taken by the other key that you inserted previously. So this is called collision. Why? Because in your hash table you do not have the space available to insert this particular key. So there are multiple ways to actually handle this scenario. So the first one is linear probing. So in linear probing, what we do is, let's say if your hash function was mod L and L is the size of the hash table, then we try to run this hash function. So our hash function becomes something like this in linear probing. Now what we do is, and this I ranges from 0 to L minus 1 technically, because so when you run this hash function for the first time, so it's same as what we had previously, right? And what did we have previously? It was h of x, correct? We had only this. So for I equal to 0, these two are same. Now for I equal to 1, when let's say there is a collision, right? When there is a collision, because you cannot insert this key here, so what you do, you run this hash function again on the same key. So 13 mod 10 plus 1, and then again you do the mod, because this value can overflow, right? So what we do here, mod L. So what it becomes is 3 plus 1 mod 10. So it becomes 4. That means what we did here, first we picked this cell, and since it was occupied, we try to pick the next cell. Since it's available, we can insert our key here. Let's say value was V1. Now what happens if we insert 23 as our key? So first we run this hash function, right? Then we get 23 mod 10 plus 0 mod 10. So it's 3. Now it's already occupied, so we cannot insert this key here. Then we, for I equal to 1, we perform the same thing. Now what happens, after this cell we try to pick this cell. Now since it's also not available, then we try to pick this cell. So if you see, if we get a collision at first index, then we slowly try to pick the first cell which is available. So this is what the linear probing is basically used to resolve the positions if you have collisions in your hash function. Now let's see another type of probing. So probing only comes into play when you have multiple collisions in your hash function. So you try to, and when a collision comes in your hash function, so what you do is, because this cell that this hash function gives, right, it is already occupied, so you need to find the empty cell. So let's create this hash table 0, 1, 2, 3, 4, 5 and 6. So this is your hash table. Now so probing is of multiple types. The first one was linear that we just saw, second is quadratic, and the third one is dual hashing. So I will not invest much time, I'll just explain the hash function and you can simply see why these are called quadratic probing. So here what we do is we take mod and then I into I, and this becomes your mod function, your hash function for quadratic probing. And here I starts from 0 to length. So if you see this, when you calculate this hash for I equal to 0, it is same as what you had previously, right? And your initial hash function was x mod L. So this is similar to what you had initially. And the third hash function, or the third way of resolving the collision, is the dual hashing. So what do you do in this case? So your hash function looks something like this: plus I into h2 of x, and then this model. And these h1 and h2 could be different or could be same, but this is how you actually resolve the collisions. When you have multiple collisions in your hash function and you cannot get the empty cell in the hash table, so this is how you can actually try to utilize different hash functions to get the empty cell. But do you see any problem in this case? Let's say you have a hash function, a hash table, right? 0, 1, 2, 3, 4, 5, 6 and 7. So let's say you were using linear probing. So after you insert, let's say the size of this hash table is L. So after you insert L minus 1 records, right? After you insert L records. So when you try to insert L plus 1th record, what will happen? Since this hash table does not have enough space, right? So you cannot insert the next record because all these positions are filled because you inserted L records, correct? Now if you insert this record, what will happen is it will try to override the value in the hash table, which we cannot do, correct? Otherwise we will lose the data. So in this case, what we will do, first we will create a new hash table with bigger space, correct? And then map all these keys into this and then insert the new key in this table. So this is what it is called the load factor. So load factor comes into play. Let's say if you keep the load factor to 0.75, that means when your hash table is 75% filled, if you insert another record and it's this percentage is increasing over 75%, then it will try to allocate bigger hash table, correct, and rehash all of your existing keys to the new hash table and then insert your new key. So this load factor is to define. So whenever you're creating the hash tables, you can also define the load factor of that hash. So I think that's it for the hashing. So now let's discuss what is consistent hashing. Consistent hashing and what problems this consistent hashing is trying to solve. So in very simple terms, consistent hashing is a technique, is a concept which allows us to distribute the data across the different nodes in such a way whenever a node is added or removed, you do not have to rebalance or reorganize the whole data set that you have. So that's what consistent hashing is trying to solve. So let's try to understand this by an example. So let's take one hash function. So it's x mod l. Now if we take the example from our previous video where what we did when we had to scale our RDBMS, what we did, we first tried to partition the data. That means we took our database and tried to split it horizontally, and now this range, I mean this partition became responsible for this set of data and another partition became responsible for this set of data. Now if still we were not able to handle this much traffic in this database instance, then what we did, we tried to organize or we tried to copy this data across different shards. So this partition goes on shard 1, let's call it S1, and this partition goes on shard 2, S2, and let's say you had another partition, let's call it partition 3, and this partition goes on another shard. Now here what happens if, so let's first understand what was the problem in this scenario. So the first one was that we assumed that each data, or let's say you have a row ID, first name, last name, date of birth, let's say you have these fields in a single record. Now you were assuming that all of these records are accessed uniformly when we try to split this data. So let's say this record had ID 100. Let's assume this goes on first shard. Let's say you have set of records on second shard, and let's say you have another set of records on third shard. And let's say this user is very active and he tries to update his profile picture or other things very frequently. So this data set or this shard, data on this shard is accessed quite frequently. Now this is okay because this is only one user and we should be able to handle it. But assume that we have many users like this one, where more of the users who are trying to update their details, their data comes on first shard only. Then what happens? This database or this database shard becomes hot. Why? Because we were querying this piece of data again and again, while other data shards that we had in our cluster, the data was not accessed that frequently from those shards. So that's why this is becoming hot shard or the bottleneck in this case. This is first bottleneck in the cluster. And what was the second problem? Second problem was, now the application, right? Let's say this was now the application which was actually connecting with these nodes, and this piece of logic which decides which record should go on which shard was in application layer, right? This app had this logic. Now assume, because of certain constraint, since you decided that this piece of data will go here, right? Let's say you said 1 to 1 million IDs will go here on the first shard, and 1 million to maybe 2 million will go on second shard. So what happens is, assume that this shard becomes full. Now what do? Let's say your data distribution was not uniform, and for some reason this shard becomes full. What do? You will have to again do the resharding on, and when you do the resharding you will have to update this logic here. Why? Because you were initially using, let's say, simple hash function, so which is mod n, and n is the number of instances in your cluster. Now you need another way to distribute this piece of data. The whole data set you have to distribute it again, right, across the different shards. So let's say you again shard this piece of data, but you cannot keep the records in these shards as is. You have to again reorganize, right? Otherwise your hash function will not be able to, how would you decide which record should go where? So you should always run a single hash function, right, on a particular key, and then you should be able to get the instance where this particular record should go. So in this case you have to reorganize the data. So here we had major two problems. The first one was hot shard, and the second one was rebalancing. Now consistent hashing exactly tries to solve these two problems in very simple terms. So let's see, what does consistent hashing do in this case? So the core consistent hashing is that it tries to map the whole range of keys. So let's say we said our keys from 1 to 1 million will go on first shard, then 1 million to maybe 2 million will go on second shard, and so on. Now every time something changes, we have to make the changes in our hash function, right? Instead, if we can somehow map these keys onto a fixed structure, so that's where the ring comes in. Here if you see what is the range here between 0 to 360. Now it doesn't matter how many keys you have, correct? Because the mapping space is always fixed. And what is that? Between 0 to 360. Now your whole key space is divided into this much range, right? So let's say initially you had only one node in your instance or in your database cluster, and this node was able to handle every request that your application was getting, and over the period of time your application became popular, and now because of traffic increase in the system, you had to shard your database across different nodes. Now before we do that, let's say you organize everything into the consistent hashing. Now let's say this is your consistent hashing. So let's say you calculated the hash of the key, it landed here, correct? So you pick clockwise first node which is available in the clockwise direction. So you picked this, again you inserted something, let's say it mapped here, you again picked this, let's say again you inserted some key and it was the hash came here, again the clockwise will pick this, since you only have one node in the consistent hashing ring, right? So everything will be mapped to only single node. Now let's say you try to add another node in the ring, right? Because you want to shard your data. So let's say you added first node at 0 and second node at 180. Now what happens? So how many keys you have to reshuffle in this case? Only the keys which came after the first node, and all these keys from here will still be mapped to the first node. So initially this key was mapped onto this application but onto this instance, but now it will be rebalanced and will be mapped here, right? So now it will be mapped here. Now let's say you insert again another record, right? Let's say the hash comes to be on this section. So again you will pick the first node clockwise. Let's say you insert again another node, so you will pick again clockwise, correct? Now again the traffic is increasing in your application, so you have to again reshard the database. So what do you do in this case? So in this case, let's say you add another node here in the ring, right? So how much data you have to rebalance when you add another node? Only this much amount of data, because this much data will still be mapped to this node and this data will still be mapped to this node, correct? So only the keys which were mapped here, right? I mean which were in this space were mapped to this application. So now instead of this application or this instance, they will be mapped on this node. So that's the basic idea of consistent hashing, that you keep on increasing the nodes in the database or in the database cluster, but you do not have to shard the whole database or whole set of data. Instead you have to rebalance a set of data. So this is the basic concept of consistent hashing. You keep on adding the nodes into the consistent hashing ring, but you do not have to rebalance the whole data set. Instead you have to rebalance a set of data set. So in our case, initially we had to only rebalance this much, and in the second iteration when we added the third node in the ring, we only had to add this much or rebalance this much. So this is the core idea. So addition or removal is okay. Addition and removal is okay, but what about the hot shard? How does consistent hashing solve the second problem of hot shard? Now let's start with our previous example. So let's say you have a consistent hashing ring, you have node 1, I mean let's write 1, then 2, then 3, and then 4, right? Now everything, let's say you inserted key 1, key 2, key 3, key 4, right? All of these keys, let's say, were mapped in this range. right? And since we said we will pick the first node in the clockwise direction, so this is the first node in the clockwise direction, so all of these keys will be mapped onto node 4. So all of them were mapped to, let's say, node 4. And since remaining nodes are still idle and they did not get the data, right? So the first thing to look at is there might be some problem with your hash function. Why? Because you are expecting your hash function to spread these keys across the ring uniformly, and since if you see all of these keys were mapped only to this range, right? So that's why there is a problem with your hash function, which is okay. But how can you actually solve this problem? Because in this case this shard became hot, right? I mean, if your hash function is not distributing the data uniformly, which usually does not happen, but in practical it can happen, right? I mean, in practical there might be chances that your hash function is trying its best to distribute the data across different nodes, but it's not possible. So what can you do in this case? So that's where the second thing of the consistent hashing, which is virtual nodes. Virtual nodes comes in. So what does virtual node mean in this case? So initially, let's say this whole range was 360, right? Because this ranges from 0 to 360. So let's say this is 90, another 90, correct? 90 and remaining 90. So this range was distributed for this node, right? And all of the keys which were mapped here in this range went on to the node 4. Instead of having this, let's say if I create another node to 3, I mean not 3, let's say something like this, and let's say I call it 3 and 2, 1 3, 1 and 4, and this becomes your 2 and 4. And now in this case, if you see, right, anything in this range will be mapped to 2, and anything in this range will be mapped to 3, or anything in this range will be mapped to 4. Now let's take the same example, right, that we had initially, right? K1 2 3 4, right? Let's say K1 maps here, I mean K1 maps here, K2 maps here, and K3 K4 maps here in this section. So what do? K3 K4 will be mapped on to node 4, K2 will be mapped on 3, and K1 will be mapped on 2. So now what you did here, right, you distributed your actual nodes onto the ring using the virtual nodes. So ultimately you split your whole range between 0 to 360 in a logical way, such that if anything falls in this, so how many initially, if you remember, right, initially this node 3, let's say, how much data it was holding, right? This range. And what was this range? 90, correct? Now if you see in this case, after we distributed the nodes using virtual nodes, right, this node is handling this much, then this much, then this much, correct? And node 3, and after this node 2, how much this node 2 was handling? 1, 2, and then 3, correct? So if you see, I mean, this was 90, right? If you equally divide this, then this becomes 30, this again becomes 30, and this also becomes 30. So in this case, each node is still handling how much space? 90 degrees, right? I mean 30 plus 30 plus 30. But now you reduce the chances, right? Now you reduce the chances to become, now you reduce the chances in such a way that a single node might not become hot, or a lot of data might not be inserted in your ring or in your node. So when you add the nodes, virtual nodes in your consistent hashing ring, then you can avoid this problem. But in general, this problem will always not go away if you have non-uniform distribution of the data in your cluster. So even after doing this, you might still face the same problem. So you also have to first see how your hash function is doing, correct? Then you need to distribute the nodes using virtual, in the virtual nodes, right? And what else? I think that's it. This is what you can do. And yeah, I think that's it for consistent hashing. So what did we learn today? We first looked at what is hash table, what are the hash functions, and then we also looked at when there is a collision in your hash tables, how can you actually resolve this? So we saw a couple of techniques. We saw linear probing, then we saw quadratic probing, and then finally we saw double hashing. And then after that we tried to understand the consistent hashing. And what is consistent hashing? Consistent hashing is a technique which allows you to distribute your data across different nodes, so that whenever you add or remove the nodes in your cluster, you do not have to rebalance the whole data set that you have. Instead, you have to rebalance a small chunk of the data. So that's where consistent hashing comes handy. And then we saw, if a particular node in your cluster becomes hot, that means more and more queries are being processed by a particular node, and still all the other instances in your application or in your cluster are still not getting enough workload. Then you can look at two things. The first one was hashing, I mean your hash function. Definitely your hash function is not performing good, and that's why you do not have the uniformly distributed data. And the second one was using consistent hashing plus distributing your nodes virtually over the consistent hashing ring. You can try to reduce this problem, but still this will not go away. So I think that's it for this video. And if you like the content, consider subscribing to my YouTube channel, and see you in the next one.